Okay, so here's a little truss that has two 10-kip loads on it up here at joint B and then at joint C. And again, it's a pretty simple truss. Every panel is 10 feet wide, so it's 30 feet from end to end, and it's 10 feet high. You can go ahead and solve the reactions on your own, but the reactions are going to be vertical at each support, the pin and the roller, and they're going to be 10 kips apiece. Down here at the pin, there is no X reaction or parallel reaction because there's no X forces on it. So that would be step number one. Typically, just like with method of joints, we want to solve the reactions. But let's say that we were asked to find a member in this truss. We are only interested for some reason in one member. And let's say that member was this member BE. It's sort of right in the middle of the truss. Okay, the diagonal that's right in the middle. Okay? What we would want to do is we'd want to cut a section through this truss, sectioning that member away from another part of the truss, or basically in this case breaking the truss in half. Okay? Now you might say, well, why did I cut it all the way through? Why did I cut the top member and the bottom member? I wasn't interested. I didn't say I was interested in those two. I only said I was interested in that diagonal member. Why did I have to cut the top and the bottom member? Because a free body diagram, remember, is an isolation of the body away from where it's supported. I can't just cut the middle member of the truss because the truss won't come apart. It'd still be connected, right? I have to isolate it, so I have to cut completely through the truss. All right? Now, what's my new free body diagram going to look like? Well, once you make a section through a truss, you can use either piece of the truss that you want. I'll choose the left-hand side, but I want you to realize I could just as well use the right-hand side. Okay? Now, how is that left-hand section of the truss going to remain there? How is it going to remain in equilibrium? Well, it's only going to remain in equilibrium if it develops forces. Okay? Now again, I've cut members that I don't really I stated I didn't want to find, but nonetheless, I mean they are they are there. BE was the only one that I wanted to find. Okay? So there's my new free body diagram. Okay, that's my new section, if you will, my new free body diagram. Okay? Now BE, this diagonal, is the one that I wanted to find. How do you propose that we find that? Is this a perfect free body diagram right now? I mean, is it in a form that you can use right away? It might be, but I usually tell people anytime there's a diagonal, I mean, you might want to think about that diagonal as being broken down into its x's and y's, right? So instead of just dealing with BE, I might want to deal with BE cosine of the angle is 45 degrees, okay? And BE sine of the angle. All right? Now again, notice that I drew BE as well as the other things that I cut, BC and FE. I drew all those acting away from this section. That's the same thing I did with method of joints. And notice, even though I'm not using the BE resultant, the BE diagonal, it was acting down and to the right, so again, I've got a downward and I have a rightward component. Okay? So, how do you want to solve this? And this is really the nice part with method of sections. It can be a very streamlined approach. How are we going to solve for BE? What do you propose that I do? How about write equilibrium equations? Okay? Where should I start writing equilibrium equations? A lot of people would say sum of forces in the x. I want you to look up here and tell me how many x unknowns do you have in this section? 3. So you can write the x equation, but it's not going to solve anything right away. How about the y equation? When you look up there for the y equation, how many unknowns does the y equation have? 3?
There's 1.
Yeah, it only has 1. And in fact, it happens to be the one that you want. You went into this problem, you really didn't care about BC or FE. You only cared about BE, right? Well, BE has a y unknown. And in fact, it's the only unknown. So the nice part, and this doesn't happen all the time, but the nice part about method of sections is once you start to understand it, you don't have to start at the x equation, followed by the y equation, followed by a moment. You might be able to start at the y equation, and you might be able to solve exactly what you want. Or you might be able to start with a moment equation and solve exactly what you want. So like this, if I say, hey, sum forces in a y equals 0, I've got plus 10 at my reaction. Okay, I got minus 10 kips up there at B, right? And I've got minus BE sine 45 degrees equals 0. Okay? Plus 10 minus 10 gives me 0. I'll take minus BE sine, bring it to the other side, it becomes positive. Hey, what can you tell me about BE? It's equal to 0. Okay? BE equals 0. So there was a problem that really, once you get rolling with this concept of method of sections, this was a problem that you could solve for very, very quickly using one equation of equilibrium. All right?